Hello everyone. Let me now elaborate about optimal control. Optimal control is a theory that seeks to find the optimal control and the corresponding evolution of state variables over time that steers or guides a dynamical system with control inputs from some origin state vector to some final state vector, fulfilling a set of constraints, including the differential equations or the differential algebraic equations or the partial differential equations that govern the motion of that dynamical system with control inputs. This is the case of an aircraft. Right? So how do I stay? And at the same time, sorry, I was forgetting, we minimize or maximize a given performance index and objective function. So typically, what we do is to minimize an objective function j made of a so-called major term or terminal term. This is the major term, which depends in general of the state values at the final time, eventually the final time as well. Imagine we want to minimize or maximize the final time, or we want to minimize or maximize the final mass of the vehicle. We will do it using a major term plus a running term between t0 and tf, right? L of xt ut principal a vector of parameters and time differential t, right? This is called the Lagrange term, right? For instance, if I wanna minimize the fuel consumption over time, I would be including here the fuel burn, right? The fuel flow differential t, integrating it from 0 to a given time. Right? If I take the integral of this, I get kilograms of fuel that I want to minimize. Just an example. Now, this is subject to a set of constraints. Which constraints? Well, first, the differential equations that govern the motion of my vehicle. Right? Think on a 3 degrees of freedom motion of an aircraft, or a 6 degrees of freedom motion of an aircraft or a spacecraft or whatever, right? And this depends on some control inputs, right? Those that are not on the left-hand side, right, which is the state, those are control inputs, and I need to define or decide what is the value of those control inputs, what is the evolution over time of those control inputs to actually make my system evolve. Those are degrees of freedom that I can find in optimal control. I can find the optimal guidance strategy, and once I set the optimal guidance strategy, the trajectory is also given as readily as a solution of the problem. Now, these the differential equations are subject to some sort of phi of xt ut p time lower or equal than 0, right? So I might have equality constraints, inequality constraints. So in the end, it's a constraint optimization problem. Imagine I tell I want to minimize fuel consumed by an aircraft in flight. I have my 3 degrees of freedom equation of motion, and I tell the aircraft that it needs to climb with a CAS profile of 280. Then I would incorporate here a quality constraint saying that some state variables need to follow some rules, right? And CAS speed must be 280 knots throughout the whole climb. Or I can also tell the system that my CL must be between the maximum value and 0. My true airspeed should be within stall speed, or greater than stall speed, and lower than divergence speed, and so on and so forth. Those are equality and inequality constraints. Then I will have an initial value. Typically, I have a final value. It can be a final value in the state variables, but it can be also a function that tells me that I need to finish in a given region of the domain. And basically x belongs to the reals, u belongs to the reals, time is a real, and the parameter belongs to parameters with which we can model the problem. It can be, I don't know, the parasitic coefficient of drag, the induced coefficient of drag, gravity, and so on and so forth. Well, this is an optimal control problem definition. The thing is that, and we're not going to go into this, you will have time to see it in air transport next year. The idea is that we can discretize this problem, discretize this integral, numerical approaches, discretize this differential equation. The inequality and equality constraints are straightforward, and I can transform this optimal control problem into an NLP problem, a nonlinear optimization problem in which I minimize some objective function, right, in a discrete fashion, right, using summatories, subject to a set of constraints. And I can apply KKT conditions, first order conditions to find candidates for the optimal, and then check second derivative information, Hessian information, to see whether there is a minimum and a maximum. Well, so this is what we're going to be doing with two aircraft that are to cross at some point. Then we will have a conflict because we will need to define a metric, a constraint that must not be violated, telling that the distance between the two aircraft must be always greater than a given value. Aircraft are going to be modeled in an easy way, right, to make things easier, but including cosinus and sinus so that we have nonlinearities. And we will see how to use nonlinear solvers to tackle this problem and eventually even more complicated ones. So thanks very much for that.